Howdy, and welcome to my first lecture on observational techniques, or more specifically, ASTR 402/602. Today, I will be discussing coordinate systems and time to a smaller extent at the end of this lecture. The reason why it is important to start with coordinates and time is because as astronomers, when we do observations, those are the two most fundamental things that we have to take into account. One, where is the object in question, and when are we actually taking those observations? Particularly in terms of what we call time domain astronomy, where we are looking at how something changes as a function of time. We certainly are very interested in knowing what time we are interested in, or what times these observations were taken. In what system was that taken? Was it taken from Earth, or was it taken from another reference point? Those sorts of things. And pardon me one second, I need to convince my cat not to sit right there, and I do this with a brush because she hates it. Yeah, yeah. There you go. There you go. Yes, brushing you. Bye bye, Luna. There you go. All right. It's the most effective way I know how to clear my desktop or clear my workspace, although her hair seems to be everywhere. All right. From an astronomical perspective, there are four major coordinate systems that we use. An altitude azimuth coordinate system, or in shorthand, alt-az system, a celestial or equatorial system, galactic, and ecliptic. These are all four systems that really depend on what you're interested in, particularly the last three. The alt-az system was the first system to be used. It's very simple, very straightforward in its understanding, but it has certain rather fundamental limitations. Equatorial system is primarily used to look at the universe itself effectively, where stars, galaxies, galactic structure, or rather, excuse me, universal galactic structure, all that sort of thing. It's the most common coordinate system that is used in astronomy. If you are a galactic astronomer, uh, galactic with a capital G, meaning that you are interested in the fundamental structure of the Milky Way galaxy, you're more likely use the galactic system. If you're a solar system uh, astronomer or a planetary geologist interested in the planets or the moon or planets or comets or asteroids, more than likely you will use the ecliptic system. These are all effectively the same type of system in the sense that these are defined by two angular measurements with respect to different reference points. And that's really the key difference between all of these coordinate systems, is how do you define the zero of one angle and how do you define the zero of another angle. We're not going to really talk about galactic and ecliptic, so I'll just, spoil it for now. The galactic coordinate system, the two frames of or 2 points of reference are the essentially plane that is marked out by the sun's revolution around the galactic center. And so that is the 0 point of galactic latitude. If you go 90 degrees up, that is positive galactic latitude. If you go down, that is negative galactic latitude. The 0 point of the galactic longitude system is the galactic center. Ecliptic, again, the zero or the plane, the latitude of that system is defined by the ecliptic, or rather the Earth's path around the sun. That plane sets the 0 point for galactic latitude. If you go up, that's positive latitude all the way up to 90. If you go down, that's negative latitude all the way down to 90. And I just realized something. Okay, good. Microphone is set to the right one. Hoping I didn't have to re-record this. Like I said, different. Oh, and also the 0 point of the ecliptic system is the vernal equinox. As these things, as I've said, are essentially the same type of coordinate system where you are measuring angles across the sky. If you need to move from one or one coordinate system to another, it is simply a coordinate transformation. And so I'll show you how you can convert from altitude azimuth coordinates into a much friendlier, much more general and usable equatorial at the end. Gets off the table or it gets the brush again. Brush, brush. Okay, good. Yeah, where was I? All right. So to first order, how do we determine what things are in the sky or where they are in the sky? So at some point, astronomers got together and decided, hey, let us divide up the night sky like a congressional map in the United States, where we make these irregular chunks around popular constellations. So, what I'm showing you on the left is the constellation boundary of the constellation of Cygnus. You can see that inside, you can these green lines trace out the popular shape that is the swan. But we also have this other region in white, where anything that has a right ascension or declination, which falls within this white region, is also considered to be a part of the Cygnus constellation. And so, for example, if someone told me that a particular object or a particular galaxy was in the constellation of Cygnus, I then know immediately that around this time of year, which is uh, or about mid-September. What day is today? Yeah, late September. Sorry, late September. The Cygnus will be pretty much above my head when the sun goes down. And so after a while, astronomers have this feeling of they know what constellations are essentially where in the sky as a function of season. And so when it comes to planning observations, we can at least start thinking about, all right, these are summer constellations, or this is a summer object, so I need to plan my observations in summer, fall, winter, so forth. This is not to be confused with an asterism. An asterism is a collection of stars either within a single constellation or among other constellations making up an object. So off to the right, Cygnus is a constellation, but Cygnus, or at least Deneb in Cygnus, is part of an asterism popularly known as the Summer Triangle, where you have Deneb, you have Vega, and then you have Altair. Vega in the constellation of Lyra, Altair in the constellation of Aquila. These are three very bright stars, and particularly in a light polluted area, they are very prominent in the night sky and very, very much make a triangle. Although, technically speaking, if you've got three stars, you're going to make a triangle. But these are three very bright stars, well spaced. It's very noticeable. So if you are on the East Coast or you are really in the United States, when the sun goes down, go outside, take a look pretty much directly overhead. You'll see three stars, hopefully, if it's not cloudy, um, and or you're outside of LA, so you can actually get out of the smog. You will see those three stars, and those are the constellations. Probably the most common or popular asterism is the Big and Little Dippers. Many people think the Big Dipper is, in fact, a constellation. It is not. The constellation is Ursa Majoris. The Big Dipper just happens to be part of the bear, which represents the constellation. Although I really want to find out where in the world there's a bear with a tail that long. I suspect the Greeks, I don't know, may have had a little too much wine when they were doing this. Who knows? The other key point to remember is that constellations, asterisms, these coordinate systems that we're talking about, or I'm going to talk about, are really a 2D representation of a 3D universe. What is important to, like I said, what is important to keep in mind, particularly if you are looking at, say, binaries or things that you believe to be gravitationally interacting in some point. There's a difference between two objects that are close to each other on the sky and two objects that are actually close to each other. So if we look at the constellation of of Orion, it makes up maybe makes up a few degrees on the sky in extent. But when you look at it in 3 dimensions, when you add the z or the a z dimension to it, you can see that the brightest stars in Orion are separated in some cases by a couple hundred light years, or in other cases by about 1,000 light years. They are, in fact, in no way associated with one another. They are not gravitationally bound. And in fact, over a very, very long time scale, because each of those stars has its own particular motion, the constellation would not be recognizable to someone today. So if I were to say in a or in a million years travel into time, the constellation of Orion, I could probably figure out that that was Orion, but it would look very funky, TM. How do we measure things in the sky? We do it using angles. And you start off with, a degree, 180 degrees moves from one horizon to the other. 360 degrees makes up the entire sphere. Examples of these: the moon and the sun both are approximately half a degree in size. The two pointer stars, as I call them in the Big Dipper, are about 5 degrees apart from each other. They're called the pointer stars because if you take the two stars and you draw a straight line through them into the north, the next bright star that you see, or reasonably bright star you see, is Polaris, the North Star. And so there are a couple of kludgy ways that you can to estimate these things using your hand. Your finger, on average, is about 1 degree. The span of from finger to thumb is 20, or pinky from thumb is 20 degrees. Your fist is 10 degrees. But again, these are very imprecise ways of doing this. When we look at the coordinates themselves, you have degrees can be subdivided into arc minutes, 60 arc minutes. So, for example, you can say that the moon is half a degree in size, or 30 arc minutes in size. You can further subdivide this into arc seconds. So each arc minute can then be subdivided into 60 pieces, and each one is a arc second. If you want smaller units, then you get into decimals. So, for example, a milliarc second is 1/1000th of a arc second. A micro arc second is 1/1 millionth of an arc second. So it becomes decimal after that. So, altitude, azimuth. Like I said, basically two two angles. One angle is you have a star in the sky, or an object in the sky. How far above the horizon, that angle is what we determine as our altitude, or the altitude of that object. Azimuth is the angle from north going through east to south to west back to north. That is the angle of azimuth. That essentially tells you what direction along the sky, in a roundabout sort of way, what that is. And so those two angles make up the alt-az coordinate system. A couple of reference points that you will need to know is that above your head is the zenith, or zenith, depending on whether or not you're Brit. And then the line which goes through north, through zenith, down to south, that is known as the meridian. So zenith is the uh, point directly overhead. And yes, I will use zenith and zenith interchangeably because of reasons. So you have the point above your head, that is zenith. The line that runs from north through that point to south is meridian. The key point with the meridian is that it divides the eastern and western hemispheres of the visible sky. Even more important to note is that the meridian, if something is on the meridian, it does two things. One, it defines your local sidereal time, and we'll get into that at the end of the lecture. But two, it is also as high up in the sky as it's ever going to get in the night. So there are a couple of problems with alt-az coordinate with the alt-az coordinate system in terms of usability. Now, it is great in terms of differential cataloging. This is essentially how Tycho did it. This is essentially how Hipparcos did it. So you determine the angle, the altitude and azimuth of a point in space at a very specific time. And then if you have the alt-az of all of the stars in the night sky, again, at that particular time, you now know the angular distance from one star to the next. The problem is you don't have a absolute reference frame because why? I'll give you a second. Why is it that the alt-az system does not give you an absolute reference frame? If you guessed because the Earth was rotating, you deserve a cookie. The night sky, the stars rise and set over time. And in fact, they do so with a period of 23 hours, 56 minutes, which is known as the sidereal rate. And so the altitude or the alt as coordinates are constantly changing. They are constantly in motion. And so again, while the positions between two stars as they move across the sky, at least to first order, do not change, the points themselves are constantly moving. And so this requires, if you want to collaborate with even someone that is a few miles away, depending on the precision of your instruments, their alt-az coordinates for a particular star at a particular time are going to be different than what you measured. Excuse me. So if you want to have a more usable or collaborative coordinate system, you then need to go to uh, an equatorial system, which is similar to this. So we kind of cribbed this from the Greeks. So the Greeks believed in something known as the celestial sphere. For them, it was a literal solid sphere of ether, and the points on it that represent the stars were all essentially at the same distance. For us, it is a conceptual model. Essentially, it is a tool through which to conceive what we are looking at in the sky. Like I said, um, we are looking at the coordinates that we are dealing with are a 2D representation of a 3D sky. The patterns are superimposed upon that celestial sphere and effectively mark out states, provinces, or what have you in that way. There are a couple of major reference points. Excuse me. You have the celestial sphere is effectively modeled off of the Earth. So if you take the reference points of the Earth and you expand them out to an arbitrary distance, the North geographic pole, basically the point at which the Earth rotates, that extended straight up is the North celestial pole. The South geographic pole stretched out becomes the South celestial pole. The Earth's equator, when stretched out to the celestial sphere, becomes, you guessed it, the celestial equator. The lines that you can see here are basically your position. If you were positioned on the Earth at that point, zenith would be uh, oriented as such with respect to the celestial sphere. Your horizon would be oriented as such to the celestial sphere as such. And so again, you can see that in order to move from one coordinate system to the other, it's simply a coordinate transformation to move from one to the other. But again, with the alt-az system, it is vital to know the time at which it is vital to know what the local sidereal time is, or what effectively is the time in your location when you are doing this transformation, because the right ascension declination is an absolute system in the sense that each star in the night sky, again to first order, has a very specific, unchanging right ascension and declination, or effectively stellar longitude and stellar latitude. I say to first order because of two different effects that are going on. The first one primarily is precession, which I'll hopefully get to later on. And the other one is proper motion. As I said before, each of these stars has their own motion with respect to each other. Given the distances involved, those motions are very, very tiny. They are typically measured on the order of milli or arc seconds per year. So, in terms of our lifetimes, these proper motions are really not going to affect our perception of things. Again, depending on the precision of your instruments, how precisely you need to know the location of something, then you need to factor that in. But precession is really the one that is most relevant in terms of what people do. It, what people who are outside of the field of astrometry or the location of things, what they need to worry about. So, hopefully, what you're getting from this is that our perception of the sky is not only dependent on time. So, for example, so as I've said, the stars rise in the east and set in the west. As I also said, certain constellations are only available during certain times of the year, and that is because of the Earth's orbit around the sun. But also, it is dependent on your location. Depending on where you are in your location, the alt as your local horizon and your zenith point are going to shift with respect to those points, the north celestial pole and the celestial equator, or the south celestial pole for those of you who are in the southern hemisphere. So, for example, if you were at one of the poles, south or north, and you looked up and you were able to do and you were to see the stars, and you were to map out what the motion of those stars look like as a function of a 23-hour, 56-day, or 56-minute period, what you would notice is that the stars do not rise, nor do they set. They simply go around in circles. Given that there is no central point in this image, I am going to say that this photo or these star trails were taken in the southern hemisphere. The northern hemisphere, as it happens, Polaris is very close, but not exactly at the northern celestial pole. Now, if you're in Ecuador, for example, I think this is in Quinto, if I'm pronouncing that right, sort of the opposite effect happens. All stars rise and set. There are no stars that are up in the sky at all times. We refer to that subset of stars as circumpolar. So if we go back to this, all of the stars in the sky, all of them are circumpolar, meaning that none of them will rise or set. In this location at the equator, there are no circumpolar stars. But for most of us in the world, we're going to see something that looks akin to this, where you have star trails around a certain point, and that certain point is at a certain altitude above the horizon. And depending on your latitude, that position is going to change because the altitude of, say, Polaris is going to be effectively your latitude. So here in Fairfax, we're roughly around 39 degrees latitude. If I were to go outside and measure the altitude of 39 degrees, at least roughly, or excuse me, if I would go outside and measure the altitude of Polaris, it would be roughly 39 degrees. If I lived in Finland, for example, I would, Helsinki, or if I lived near Helsinki, then I think it's like 45 degrees. Yes, I'm American, so I don't know where things are. So Polaris would be significantly higher up in the night sky. And so more as you get to higher and higher latitudes, more and more of the sky becomes circumpolar. This is important from an astronomical point of view in that if you know that an object is circumpolar and you're not really picky as to how high it has to be, then you know that you can basically observe this at any time you want to, at any point in the year. It will always be available, regardless of season. So, this is a question for you to ponder on your own. A circumpolar star is observed to have an altitude of 49 degrees, 38 seconds, excuse me, 49 degrees, 38 minutes at upper transit, and an altitude of uh, 18 degrees, 21 uh, minutes at lower transit. Now, what does upper transit and lower transit mean? Now, again, you have the meridian. The meridian goes from north through your zenith down to the south. So imagine, again, I can kind of see a Polaris in the or a bright object in the center that kind of isn't moving. I don't know if you can see my cursor or not, but that's essentially that is Polaris, and so I know this photograph was taken in the north. Excuse me. So I would draw a line from the horizon through Polaris up towards my zenith and then back behind my head. I mentioned before that the meridian is where the star is going to be as high up as it's ever going to get in the night sky. I should have made the caveat that that is the case for all stars that are not circumpolar. Circumpolar, at least at the anywhere between the poles and the equator, you're going to have essentially 2 points of transit where it moves from one hemisphere into the other one, from east to west or back again. The upper transit is when it moves from east to west. That is when it moves across your meridian um, at above Polaris, and then the lower transit is when it moves from west to east below Polaris. So getting back to this question, so you have the altitude of the star as it moves from east to west, and then you have the altitude of the star as it moves from west to east. If we assume that these are true altitudes after correction for refraction and instrumental effects, what is the latitude of the observer? If you're going to do this, what you would really need to do is you would need to calculate um, the angular distance between these two points, and then cut that in half, and then add it to the bottom one. If you'd like to make a guess at this, please, by all means, put your answer in the comments section. Equatorial coordinate systems. I mentioned these two terms before, right ascension and declination. Um, these are basically fancy terms for longitude and latitude. So right ascension corresponds to a stellar longitude, declination corresponds to a stellar latitude. Declination is defined from the celestial equator, much like latitude is defined with respect to the equator. Positive declination corresponds to north. Negative declination corresponds to south. Right ascension is a bit weird, primarily because this convention came about because, as I was talking about before, there is a periodicity, or excuse me, there is um, a temporal nature to, yeah, periodicity. There is a temporal nature to where the stars are with respect to a certain observer. If you were to track the position of Vega from where it is on the meridian, if you waited 23 hours and 56 minutes, it would set, the sun would be in the sky, it would rise, and it would come back to the meridian at that point. And essentially, you can think of that at the point of east, it is ascending into the night sky. And so this idea of right ascension is the idea of the angle over which, or the time at which, it ascends as it moves through the sky. And so unlike all of the other coordinates, right ascension is actually given in hours and minutes and seconds, as opposed to degrees, arc minute, or degrees, minutes, and seconds. The 0 point for the right ascension is measured where the ecliptic moves from the moves across the celestial equator, as measured from east or west to east, effectively when the sun is moving from the southern hemisphere to the northern hemisphere. Or in simpler parlance, it is also the vernal equinox. I think that's stated. One thing I want to state here, and I may state it again later on, but it is an important thing to note, is that, as I said, right ascension is determined in terms of hours, minutes, and seconds. That is not exactly, I mean, it is, but it's not an angular unit that you're familiar with. Most of us are going to be familiar with either degrees or radians. So, how do I put hours into that? Well, if you think about it, our day is split into 24 hours. Basically, it's based on the sun. It is a synodic period where you have, again, roughly 24 hours from when the sun is at high noon when it comes back to high noon again. You might want to start thinking about why those two periods are different. Why is it that the sidereal period is 23 hours, 56 minutes, and why the solar period or synodic period is 24 hours? Again, pretty much. The sun's motion actually is actually much more complicated than you might imagine. But that is beyond the scope of this particular lecture. But there is a definitive 4 minutes, approximate 4 minutes difference between the two. You might want to start asking yourself why that might be the case. So, 24 hours over 360 degrees. What that means is that in 1 hour of time and in 1 hour of right ascension, that corresponds to 15 degrees. So, to first order, it depends on declination, but to first order, if you are looking at, if you have a star that has that is 15 degrees above the horizon, and you want to know how long you have to wait before it gets to the zenith, it's effectively, uh, it has to go, uh, that's 1 hour, it's about 4 hours, excuse me, 5 hours to get to the meridian. Take 70, 75 degrees divided by 15, that gives you 6 or so. Um, yeah, I'm real good at math, but trust me. So 6 hours up, 6 hours down. Again, it depends on depends on your declination. But the take home point here is that right ascension is really the reason why right ascension is given in hours is again because it is useful in terms of timing of when objects are going to be in which parts of the sky. And if you want to convert from right ascension into declination, you have to multiply your right ascension times 15, and that includes minutes and seconds. So if you had 1 minute of right ascension, that actually corresponds to 15 minutes of angle. So vitally important if you want to convert from one thing to another in terms of degrees. All right, and so this basically talks about what I was just talking about. The sky turns 15 degrees per hour, um, and RA is in terms of 0 to 24 hours. 1 hour of is divided by 1 hour of angle is divided by 60 minutes of arc. 1 minute of arc is divided by 60 seconds of arc. But again, if you want to convert from that into uh, basically degree angles or a degree unit, then you have to multiply by 15. As I mentioned before, different constellations are available at different times of the year, and that is because the Earth orbits the Sun about 1 degree per day, and so we are only able to see those constellations that are in this part of the sky that we can observe that does not have the sun in it, or basically are only out during the night. So those constellations that are on the opposite part of the sky as the sun. We have 4 points of interest. We have the vernal equinox, the summer solstice, and the autumnal equinox, and the winter solstice. Now, what took me for a second here is the RA of the vernal equinox is 0. The RA of the solar solstice is 6 hours. The RA of the autumnal equinox is 12 hours, and the RA of the winter solstice is 18. But what this is showing you, what this label is basically what the observer cares about. It cares about what is the RA on the meridian on those dates. So if you are interested in an object uh, in or about the vernal equinox, then you want to look in the RA range of around 12 hours, plus or minus 3 hours in my experience, is a good range in terms of being able to see the object over time. Now, if it's and again, as the stars move across the sky, the RA increases. So something that is, uh, if you're at local midnight, vernal equinox, the RA is 12, right along the meridian. If you wait an hour, the stars along the local meridian are 13 hours in right ascension. So if you do minus, if you're looking at something that has a right ascension of 10 hours on the vernal equinox at midnight, then it is setting. So one would want to keep that in mind when choosing objects for observation. Summer solstice, objects on the meridian at local midnight have an RA of 18 hours, and so forth. One of the reasons why we have seasons is not because of, or the primary driver of seasons is not distance to the sun. That is a factor, but it is not the primary driver of seasons. The primary driver of seasons is the tilt of the Earth at 23.5 degrees. What that does is that the sun's altitude is going to shift by as much as 27 degrees. It's going to have a declination of positive 23.5 degrees at the summer solstice and negative 23.5 degrees on the winter solstice. That does two things. One, if it's as it is higher up, it is going to spend more time in the sky, meaning our daylight hours will be longer. And two, the sunlight is more direct onto your position, and so therefore the energy of the sun is concentrated, which allows for more efficient heating. And then the opposite effect is when the thing is when the sun is in the south, when it is winter solstice and the sun is 23.5 degrees below the celestial equator. So here are some questions to ponder as well. Again, you can put the answers to these in the comment section. What is the right ascension at the winter solstice? Can you find it on one of these two globes that I've got up here? What is the maximum declination the sun reaches? When does the sun reach that declination? Fairfax, Virginia, the latitude is 38 degrees, 50 minutes, 4.9 seconds. What declination is overhead? Meaning, what is the line of declination that passes directly through the zenith? Now let's talk about that other thing that I was talking that the other aspect of why right ascension and declination coordinates do change over time for a particular object. I mentioned proper motion, the motions of the stars with respect to each other. That is a small effect. The primary effect is due to the precession of the Earth's tilt, or the precession of the equinoxes as termed by Hipparchus. What he noticed was that the point in the sky where things rose on the vernal equinox changed over the course of the year. And we have since refined this and determined that the precession of the Earth's axis, basically as it moves around, similar to that of a top slowing down, it's around 26,000 years. So at the moment, it is simply a happy accident that Polaris is our North Star. It's about, I want to say, about 8 or 9 minutes off of true north. During the time of Tycho, it was actually further away from. Uh, I may have that backwards. It, it was noticeably different. I think it might have actually been closer. You can Google that if you would like. But over the course, definitely over the course of serious astronomical observations of the position of Polaris, Polaris's position with respect to celestial North Pole has measurably changed. In about 15,000 years, the North Star is going to be around Vega or so. I don't believe Vega is going to be nearly as north as Polaris is, but Vega, the brightest star in the constellation of Lyra, which currently is best seen in the summer, that will actually be the northern star, or the north, yeah, the North Star. And so what this means is that we need to update the right ascension and declination. And then the age of computer, or the age prior to computers, we refer to these things as epochs. And so what was published was that in 1950, you had a coordinates, a right ascension and declination of all stars for when the stars were observed in 1950. And then they corrected it in 2000 for precession and gave another list of what the right ascension and declinations are for each individual star. If you were to go to an astronomical database like Simbad, what they will give you are effectively two epochs. They will give you the 1950 right ascension and declination, and then they will give you the epoch 2000 right ascension and declination. Well, as it happens, oh, and again, before computers, you would know the rate of we know what the rate of precession is. You would then have to correct from either 1950 or 2000, depending on how close you were to either of them. Well, I should say rather after 2000, you would correct to 2000. Prior to 2000, you would correct from 1950. Now, computers can do that for us. So what we have now termed is the current epoch. So if you were to use a program like the Sky, the right ascension declination that it gives you is in the current epoch. So it is constantly being updated due to the uh, due to the due to the effect of precession, and you would correct for these using a rotation matrix, or basically coordination. So, um, why would you want to get right ascension and declination from Altaz? Well, um, one way is, so I am currently doing an experiment where I have a small solar telescope, and I am measuring the angular size of the sun, as often as I can, weather permitting and schedule permitting. I am measuring the position of the sun in terms of altitude and azimuth. Now, if I have the time of the observation, I can then calculate what the right ascension and declination is. This will make it far easier for me to be able to plot out an orbit, to figure out where the Earth is with respect to the sun, if I know where the sun is in an absolute reference frame compared to a background field of stars. And so again, I would need to know I guess this is to go from right ascension to alt and as. So I would need to know my latitude. I would need to know, again, the time, which would give me the hour angle. I'll explain in a moment. And then I would need the coordinates. And so this is going back and forth. Now, why would I want to know alt as from right ascension declination? From an observational point of view, that's pretty straightforward. That tells me not only when, or not only, well, that tells me where in my local sky the star is going to be. How high is it going to be above the horizon, and where in cardinal direction it's going to be above said horizon. And so I can then compute over a variety of time effectively where what that altitude and azimuth, how that altitude and azimuth is going to change over the course of one particular night. Hour angle. What is hour angle? Hour angle is the angle with reference to the meridian. Negative in terms of writing, positive in terms of setting. I knew I should have trusted my gut on that one. So, so what that means is if you want to know what your local time is, local sidereal time on the horizon, and you know the RA of your object, you would simply add your hour angle to it. That is effectively the angle to the meridian from the RA, and that again is also dictated. No, that is not. Um, Again, that is the angle from the meridian. Here are the lovely equations that you can use in order to actually do that calculation, or to change from right to get from right ascension declination to alt as, and um, you can do a similar sort of coordinate transformation in order to get from alt as to right ascension and declination, to flip from one to the other. I mentioned this before. Galactic coordinate systems. Um, this is for astronomers who are specifically interested in the galactic structure itself. Rarely, if you are interested in just simply a particular star or a particular cluster, rarely do you use galactic coordinates unless, again, it is tied to some kind of investigation in terms of the galaxy, the overall galaxy itself. Some questions here. At approximately what galactic coordinates would you expect the density of stars in the sky to be highest? So again, just to remind you, the galactic coordinate system is constructed such that the galactic equator is defined as the sun's motion around the galactic center. This is effectively the disk of the galaxy. The Milky Way galaxy, just to remind you, is a spiral galaxy, meaning that has a bulge or center of fairly spherically concentric ball, or a ball of stars, spherically symmetric ball of stars, surrounded by a relatively thin sheet of stars that are spread out and shaped like a disk. And we are embedded within that disk. Declinate or galactic latitude is positive if you go towards the North Galactic Pole, and then South Galactic Pole. And the galactic center is the center of the galaxy. Basically, it's in Sagittarius. So, at approximately what galactic coordinate would you expect the density of stars to be densest in the sky? Approximately what direction might you expect to see the highest density of globular clusters? The third structure that I failed to mention is the halo. The halo of the Milky Way galaxy is a spherical distribution of globular clusters. Now, time. Basically, record keeping. We have a variety of different ways to keep time, and sadly, not as uniform as we would like, at least from a terrestrial standpoint. I just learned actually that the timekeeping for the moon is also not standard. They are still trying to figure out how a loony, or someone on who lives on the moon, would what their clock would say with respect to the Earth, because there are different types of times. For astronomers, when you're talking about time of day, we use what is known as UTC, or the universal time. What that means is that is the time at which the clock at the Royal Observatory in Greenwich, England, that is what that time is. So whatever that clock says is the universal time across the entire globe. Yay, British Empire. So that's UT or UTC. Another way that astronomers will keep time is through what is known as the Julian date. So while UTC allows us to determine the time from a absolute standpoint of what time is it on your part of the globe, in terms of calendar year, we have what is known as Julian date. Because again, while we use the Gregorian calendar here in the West, other cultures do not use that. Chinese, for example, do not use it. The Arab nations do not use it. So, and also on top of that, because of that whole pesky 326 point or 365.25 day thing and the whole leap year business, um, trying to keep track of things by month, day, and year is problematic. So we just simplified it. We chose a point in the past, January 1st, 4713 BC to be specific, and we have just counted forward from that point. Why that date? I don't know. The story that I got was that there were three particular tax seasons in a particular culture, and those tax season that was the date that those tax dates lined up. So effectively, that was the date that everyone dreaded because that was when you had to pay taxes three times. Is that story true? Probably not, and I haven't bothered to look it up. If any of you are interested, I'm sure you can Google it. But that is how we define Julian date. So right now, Julian date is 2000. Excuse me, 2,460,569. So that is, if you were wondering, how long has it been since January 1st, 4713 BC? It has been 2,460,569 days. The decimal points indicate the seconds were relative to that noon point. And so if you're really wanting to know, if you have a specific date in mind, then you can use that formula to figure it out. Now, when you're actually doing time domain astronomy, when you're actually talking about looking at how something changes as a function of time, writing down 2,460,000 yada yada, that gets tiresome and it gets really annoying to read graphs that way. So what we use is what is known as the modified Julian date. And you can modify it however you want, so long as you tell people how you did it. What I do is if you're looking at something that has a period or if rather an observing window where you've only observed something, prior to 100 days, I lop off everything but the last three digits of, in this case, 544 and anything like that. And I just put down this is the Julian date plus 4 million or 2,460,000 or what have you. If you are looking at something that spans thousands of days, then obviously you would cut it, or you would truncate it as appropriate. Sidereal time. Again, sidereal time is defined as the time at which sidereal time, local sidereal time, is defined as the meridian. One more time. Click three. Local meridian time. Take four. Local sidereal time is taken as the right ascension that is currently on the meridian at that moment in time. So if you were standing outside at midnight and Vega was right on your meridian, then I believe, if memory serves, your local sidereal time would be 18 hours and 50 some odd minutes. And the angle, our angle is the angle between the two, um, between the object and the meridian. Now, let's talk about where do you measure time from? You might think that would be fairly straightforward. Do you measure? You would measure time from the Earth as observed from the Earth. Well, as I mentioned before, and I think I don't. For some unknown reason, I don't have this listed. Before I asked you how to, or I don't have a slide on this. Before I asked you the difference between sidereal and synodic time, what is the physical phenomenon that differentiates between the two? And that is from what object you are measuring that particular time or that particular period. If you are measuring with respect to a background field of stars, then that is a sidereal period. If you're measuring with respect to, say, the sun, that is the synodic period. So the period of the Earth's rotation is 24 hours from the synodic period of the Earth's rotation is 24 hours. Its sidereal period of rotation, which I would argue is its intrinsic rotational period, is 23 hours, 56 minutes, as defined by a fixed coordinate system described by the stars in the night sky. If you look at the moon's period is roughly 27 days. The moon's sidereal period is roughly 27 days because it takes 27 days to go from, say, being aligned with a certain background star all the way around to being aligned with that same background star again. Again, I would define that as the true intrinsic orbital period of the moon. That is how long it takes to complete one cycle around the Earth. Now, its synodic period is roughly 29 days, or closer to a full month. And what a synodic period is the time it takes to go from one particular phase to the next time it is in that particular phase. So the time it goes from full moon to full moon. The reason why that roughly 2 day difference is because the Earth has moved with respect to the sun and the background stars in its orbit. And so it takes approximately 2 days for the moon to continue in its orbit to get back to an orientation where you have moon, Earth, sun directly in a line. When you talk about periods of planets, those are all sidereal periods, because in this case, you are not looking at the period of the object as seen by the Earth, you are looking at that period as seen by the sun. So a sidereal period is defined by an observer on the thing that is being orbited. But what about this thing I have in the slide called barycentric motion? Well, one of the first ways that the speed of light was measured was because a dude by the name of Romer was looking at the orbital periods of Jupiter. Because if you know the orbital periods of the moons of Jupiter, he was looking at the orbital periods of the moons of Jupiter, I think Io in specific. If you know those orbital periods, you can then work out the mass of Jupiter. And what he noticed was that the period measurably differed depending on what time of year he was actually doing the observations. And the reason for this? Light travel time. The speed of light is a constant and it is finite. And so, if we are, depending on where we are from Jupiter, as Io is going around, it's going to take longer for the light to get to us from one position, or it's going to take shorter depending on where we are in relation to Jupiter. If we're moving away from Jupiter, then the period is going to be longer. If we're moving towards Jupiter, the period is going to be shorter. When we are dealing with things that are orbiting around other things, like, for example, binary stars or exoplanetary systems, the same effect can be seen. Our orbital motion around the sun is going to affect the periods that we measure. And so the fix that we have decided on is measuring these periods with respect to the barycenter of the sun the Earth-Sun system, or more specifically, rather, the barycenter of the solar system. And you can see that this notion that the sun is fixed in space over all time as Earth orbits around it is not accurate. And so you can see over the years that if you look at this in terms of the vernal equinoxes to the right, so you have, yeah, so this is 360 degrees or 24 hours in well, let's look at 360 degrees in ecliptic coordinates and ecliptic latitude or ecliptic longitude. You can see the sun changes its position relative to that center point quite dramatically as a function of year. And that is because, again, of gravity. The different planets, most notably Jupiter, the gravitational influence of these worlds are affecting the sun's position relative, again, to a background field of stars or background reference point. It is exactly this. Uh, it is exactly this that allows us to actually observe planets in the first place through a technique called the Doppler effect or radial velocity technique. Because as an object is moving towards us, then we can see the light from that object get bluer as it moves away from us, the light from that object getting redder. If a star was fixed in space as it has things orbiting around it, then it would display no change in its Doppler, no change in its radial velocity. It would have a velocity which was dictated by the velocity away from or towards the Earth. But because of the gravitational influence of a planet going around it, that star will wobble. And so we can measure it. So if we are interested in the finding accurate periods or precise periods of planetary orbits, we want to know what precise periods of Cepheid variables are, if we want to know what the precise the periods of eclipsing binaries, things of that nature, then we take that, we convert our times that we measure or that we record into a frame that is based on observers at the barycenter of the Earth-Sun system at that particular time. All right. And then finally, what we have is what is the angular separation between two objects? Can I move my face? I don't know if I can move my face. Yeah, I can move my face. So, for example, I was talking about before with the alt-as system. That is a relative system in that you can tell what the distance between two objects is relative to another object. Now, the way to do that is to use the spherical trig. Now, the equation is the cosine of the angular distance between two objects is equal to the sine of the declination of the first object times the sine of the declination of the second object, plus the cosine of the declination of the first object times the cosine of the declination of the second object times the cosine of the difference in right ascension. So again, to keep everything, keep comparing apples to apples, you will need to convert right ascension, which is in hours, minutes, seconds, to degrees, minutes, seconds, or decimal degrees, or decimal radians. So you will need to convert that into the same units as you have for declination. Now, this is the distance between two objects on a sphere. So if you have two objects that are well separated on the celestial sphere, then that first equation is a must. But very much like we had the small angle approximation in planar trigonometry, you also have a small angle approximation in spherical trig. And so if you have two objects that are My For what I'm comfortable with, if the two objects are within 30 arc minutes of each other, then I would say that uh, this formula is applicable. If you have questions as to whether or not that corresponds to a small enough angle, well, just use the top one. But there you go. You had the small angle approximation for that. So if you want to know this type of observation, or at least this type of equation, is vital in observational astronomy in terms of determining the fields of view of telescopes and camera systems. Obviously, it'll tell you what the separations between two objects are, but it is, at least for myself, it is primarily used to determine the what we call the plate scale of a camera. Effectively, how big a chunk of the sky can you see in one exposure of your camera attached to your telescope? And then you can calculate what the angular separation between two objects is, and if that angular separation is smaller than the field of view of your camera, then you can observe both objects at the same time. And then lastly, I'm going to put this up, that RN deck can come in various different notations. You have what is known as the sexagesimal system, which is hours, minutes, seconds, or degrees, minutes, seconds. You can write it as with colons in between. You can write it in terms of hours of H, M, and S. And then you can also write it in terms of decimals. Um, on that. Declination has a sign because, again, that differentiates between northern and southern hemispheres. But because we're going from 0 to 24 or 0 to 36, right ascension is always positive. These notations are something to keep in mind because depending on the catalog, uh, depending on how the catalog that you're using or the code that you're writing, how it actually differentiates between these values within right ascension declination can vary. Some catalogs you need the colon, other catalogs it's pretty free form, so long as it's in one of these particular formats. All right. Well, I actually have to run and teach a lecture in person. Well, actually, it's going to be on Zoom, but you don't really need to know that. What you need to know is that I got to go. So, thank you for watching this lecture. The next lecture in this series is going to be on radiation and light, and I'm hoping to be able to have that posted within the next couple of days. So, with that all being said, peace out and clear skies.